going to close out our discussion of graph theory with a fairly short video, especially compared to the last one, just about counting paths. Suppose we have a graph and we want to know not just is there a way to get from one vertex to another, in other words, are they connected, but in fact, how many ways can I get from one vertex to another? Can we count how many walks there are that connect two vertices? In an undirected graph, the answer is either 0 or infinity. If there's a way to get from vertex 1 to vertex 2, then you could get there and then turn around and go back to V1 and then go back to V2, and you can do this over and over again. And technically these are different walks. It's very long compared to the one we started with, but in a technical sense, it's a different list of edges. So instead, we're not just going to ask how many walks are there. We're going to ask how many walks of a specific length, how many walks that use a specific number of edges. So is it possible to get from vertex A to vertex B in exactly 3 edges? If so, how many ways? Is it possible to get from A to B in 4 edges? If so, how many ways? Etc. What this brings up is a connection to linear algebra. So for example, suppose here's our graph. How many paths of length 1 are there connecting vertex 1 to vertex 2? Well, there's one of them, okay, because it has an edge. How many paths of length 1 are there from vertex 1 to vertex 3? None of them, okay? It doesn't have an edge connecting them. So while they are connected, I can get from vertex 1 to vertex 3. I cannot do so with a single edge. And how many paths of length 1 are there from vertex 3 to vertex 4? Well, there's 2, because there are 2 different edges that connect them. So what we do is we make a matrix in the following way. If we had n vertices to begin with, we make an n by n square matrix, and A sub ij is going to be the number of edges that begin at I and end at j. In an undirected graph, it doesn't actually matter whether you begin at I and end at j or the other way. But in a directed graph, it might be different. In other words, the matrix we're making for an undirected graph will be symmetric. The matrix we make for a directed graph might not be. This is called the adjacency matrix of a graph, and what it really does is it counts how many edge connections are there between two vertices, and it actually counts them with direction, because aij is how many edges from I to j, aji is how many from j to I, and in a directed graph, those might not be the same thing. So what about the graph we have above? Can you construct a 4x4 matrix that keeps track of how many edges connect one vertex to another? Here it is. How many edges connect vertex 1 to vertex 1? None. 1 to 2, a single edge. 2 to 1, a single edge. Notice that since this is an undirected graph, the matrix is symmetric. A sub ij is always equal to A sub ji. Observe these 2's. Vertex 4 to vertex 3 or vertex 3 to vertex 4, there are 2 connections. What do adjacency matrices have to do with counting paths? So, the adjacency matrix shows which vertices are connected to which and how many times. We've already remarked that the matrix is symmetric for an undirected graph. If it's a simple graph, then the entries can only be 0 or 1. If there's not multiple edges, if it's not a multigraph, either vertices are connected or they aren't. Loops show up as entries on the diagonal. If vertex I is connected to itself, then you have a loop that will show up on the diagonal A sub ii. So neat, I mean, okay, we can transform a graph into a matrix, but so what? So let's try to develop an inductive procedure for counting paths from one vertex to another, specifically vertex I to vertex j. The base case is a paths of lengths 1, and that's just the adjacency matrix. How many ways can I get from vertex I to vertex j in a single step with a single edge? That's the adjacency matrix. Now let's suppose I have a matrix B. B sub ij is specifically the number of paths using k edges that go from vertex I to vertex j. So the adjacency matrix would be like matrix B, where k is equal to 1, paths of length 1. Let's just pretend I have a matrix which counts paths of length k, the number of k length paths from vertex I to vertex j. That's how I make my matrix B, for the sake of argument. Well, how would I go about counting k plus 1 length steps from vertex I to vertex j. All right, where are we? So far what we've done, if I have a graph on n vertices, I can make an adjacency matrix that counts the number of paths of length 1, aka edges. Now we've also inductively assumed that for some k, I have a matrix B that counts paths of length k from vertex I to vertex j. We're now going to count paths of length k plus 1 from vertex I to vertex j in a specific manner. Maybe, starting at vertex I take k steps to get to vertex 1, and then I take a single step from 1 to j. So overall, I took k steps to get here, and then one more step to get here. I have a k plus 1 length path to get from I to j. Or maybe k steps start me at I and get to vertex 2, and then a single step to get from 2 to j, and so forth until the last vertex. From vertex I take k steps to end up at vertex n, and then a single step to get from vertex n to vertex j. Altogether, to describe k plus 1 length paths from I to j, I've said, well, where am I after k steps? Maybe I'm at 1, maybe I'm at 2, maybe I'm at 3, maybe I'm somewhere, and then I take one more step to end up at vertex j. So, what does this actually do? B sub I1 is how many paths of length k get me from vertex I to vertex 1, and A sub 1j is how many paths of length 1 to get from vertex 1 to j. Here I have the number of paths of length k to get from vertex I to vertex 2 times the number of paths of length 1 to get from vertex 2 to vertex j. We're splitting this up as a multi-step task. First, how many ways to take k steps and go from I to 1, and then how many ways to take one step to get to j. Or I could have done how many ways to take k steps to get from I to 2, and then how many steps to get from how many ways to take a single step to get from 2 to j. Or, and so forth until finally, how many ways to take k steps to get from I to n, and then how many ways to take one step to get from n to j. And if I add all these up, I will have counted all the ways to take k plus 1 steps to get from I to j by breaking it up as a two-step procedure, I to an intermediate step in k steps, and then that intermediate place to j in 1. The matrix B was counting k length paths. The matrix A counts 1 length paths. What we've really done is computed the product of the matrix B times A. Bi1 A1j, Bi2 A2j, add all this up. That is the ith row of matrix B. Notice that this I is staying the same, times the jth column of matrix A. This j, this second entry for A, stays the same. Ith row of B times jth column of A is exactly how we would get the ij entry of this matrix product. In other words, if I multiply these matrices together, each entry will tell me how many length k plus 1 paths are there connecting various vertices to one another. So we're now prepared to present a solution to this path counting problem. Here it is. Suppose we have a graph G with an adjacency matrix A. Then the number of paths, specifically of length k, connecting vertex I to vertex j is given by the ijth entry in the matrix A to the k. We're going to prove this inductively. The base case is paths of length 1 connecting vertices to one another, and that was the definition of the adjacency matrix A, which is, of course, to the first power. Now let's inductively assume that A to the k specifically counts paths of length k connecting all the vertices to each other. From our previous slide, we know that if we have a matrix that counts paths of length k, multiplying it by A will produce something that counts paths of length k plus 1. So something that counts paths of length k times A is guaranteed to count paths of length k plus 1. But of course, A to the k times A is A to the k plus 1. So inductively, if A to the k counts paths of length k, then A to the k plus 1 counts paths of length k plus 1. That's it. The real work of the proof was actually on the previous slide. Okay. So powers of the adjacency matrix can be used to count paths of different lengths. Let's take a look at an example. In the graph we started with, how many ways can I get from vertex 3 to vertex 1 using 7 steps? So for example, to get from 3 to 1, I could do 1, 2, 3, 4, 5, 6, 7 steps. That's one possible way. Or maybe 1, 2, 3, 4, 5, 6, 7. That's another 7-step path to get from 3 to 1. Well, to solve this problem, all we have to do is make the adjacency matrix. We already had it from a previous slide. Then we just need to raise it to the 7th power. We're going to use a computer to do so. Here it is. And since we're trying to go from vertex 3 to vertex 1, we just look at the entry row 3, column 1, which is 146. So rather than actually try to count them all by hand and probably lose track and have duplicates and not count them all, etc., we just know there are 146 different ways to take exactly 7 steps connecting vertex 3 and vertex 1. Let's look at another example. Here's a directed graph. What this means is that the adjacency matrix will probably not be symmetric. Let's find how many ways to get from vertex 3 to vertex 1, specifically using 10 steps. Now, directed graphs and longer paths can be more complicated to do by hand. So maybe from 3, I'm trying to get to 1 in 10 steps. Let's go 1 step, 2, 3, 4, 5, 6, 7, 8, 9. Now I can't actually get there. It can be tough to just do this by hand. So let's just make the adjacency matrix. Notice it's very much not symmetric. I've got a loop from 1 to 1, so a sub 1, 1 is 1. I do have a single arrow from 1 to 2, so a sub 1, 2 is 1. There is no arrow from 1 to 3, so a sub 1, 3 is 0, and so forth. Okay. Observe we have some unsymmetric bits here, so like a sub 3, 2 is 2. There are 2 arrows that go from 3 to 2, but there are no arrows that go from 2 back to 3, so a sub 2, 3 is 0. But here's our matrix. If I raise it to the 10th power using a computer, we get this. I want to go from vertex 3 to vertex 1, so I look at the 3rd row, the 1st column, 644. There are 644 ways to take a walk of length 10, starting at vertex 3, ending at vertex 1, respecting the arrows of this graph. So pretty remarkably, these powers of adjacency matrices make very short work of this issue of counting paths. A nice little connection to linear algebra that you might not have expected lurking in the background of graph theory.